Hello, I'm Alexandre Bonvin. I'm a professor of chemistry at Utrecht University, and I'm working in the structural biology field, trying to understand how molecules interact with each other. One of the techniques which is providing important information for this kind of studies is NMR. NMR is not very well known and it's considered rather complicated. But if I tell you MRI scanners in hospital, usually everyone has heard of them. In MRI scanners, you put people in a strong magnet and you make pictures of them. In NMR, we put molecules, proteins in our case very often, in very strong magnets, and we also make pictures of them but in different manners. We look at them at atomic details. In NMR, what we are doing, we are looking at properties of atoms, nuclei, small nuclei, which behaves like small magnets. When you put them in a magnetic field, they are lined along the field. In the same way that a compass in a magnetic field of the Earth gives you the direction of the north. Now we can put energy in the system and we perturb those small magnets. And from the response that they are giving us, we can record what is the response from those magnets, and we can get information. Basically looking at interactions between molecules, the network of life, what I like to call the Facebook of life.
My name is Gert Volkers. I'm a biologist by training and I work in the NMR spectroscopy group. So today we will try to select a target of biological relevance for which we want to understand more about the structure and function. The chemicals for which we are talking about today are the so-called non-steroid anti-inflammatory drugs, NSAIDs. It's a complicated name, but all of you probably know chemicals like paracetamol, ibuprofen, diclofenac. If you look at the structure of, for instance, aspirin, ibuprofen and diclofenac, if you compare them, they do not look a lot like each other. Still, they have the same mode of action, namely to inhibit function of a certain protein. Here you see an example of aspirin bound to a protein. The protein is composed of alpha helices, beta sheets and loop structures that together make sure that the protein can do its work. If you zoom in on the aspirin molecule bound to the protein, you can clearly see that it makes all kinds of contacts to the rest of the protein. This makes sure that the molecule is tightly bound to the protein of interest and thereby inhibits the function of this protein. Okay, we have successfully transformed our plasmid into the bacteria of interest. So now we will pick a separate colony here and transfer that to our culture medium so that we can start to culture our bacteria. We have now cultured our bacteria, we have collected our bacteria, subsequently lysed the bacteria, and now we have our bacterial lysate, which we will use to purify our protein. So what we have to do first is put our protein sample on the machine. Now, this machine allows you to purify your protein of interest on the basis of an affinity tag that we have built in our protein of interest. So what we will do, we will activate this machine, which will then start to purify our protein over this column and will subsequently be collected in the fraction collector. Here, after a run, you will get your protein of interest. So if we now look at the chromatogram, you can see here we load our protein sample containing all the proteins of bacteria, And after extensive washing, we end up with an illusion of the protein of interest. If we then take this protein, we see here a sample that contains our protein. Almost ready to go for the NMR. The only thing we have to do now first is concentrate this sample using an ultrafiltration device. This allows you to bring it down to a relatively small volume, for instance 300 or 400 microliter. After that, we will transfer our sample to a sample tube, and that allows us to measure using NMR spectroscopy.
Hello, my name is Klaas van Hoeve. I'm an assistant professor here in the group and facility manager of all the magnets that here are around. We're standing here at an 800 megahertz machine. The higher the magnetic field, the higher the resolution of our spectra. So what do we put in? A tube with a solution, a protein solution, or sometimes a rotor, which can contain a solid protein, like a protein in a membrane, or an amyloid fiber, and these we put into the magnet on the top. So our protein is now in the magnet, and we can imagine that this is a protein built up of different amino acids connected by a backbone with blue ribbon. And if this protein is structured, the environment of each of the amino acids is different. So each amino acid will have a different frequency in our NMR magnet. So here you see that each peak has a different frequency in both dimensions, meaning that this protein is structured. All amino acids have a different frequency. While this is a spectrum of an unstructured protein, where in this dimension almost all signals have the same frequency. We call this assignment of the spectrum. So if we know that this one is, for example, this one, and this one is this one, we can now record other types of spectra that correlate amino acids. And if we know that this one is close to this one, and this one is close again to this one, if we have enough distances, we can use this into a computer program and calculate the structure of a protein. What you will see is that some signals will change and some stay the same. If you then zoom on it and do this addition of the drug in steps, you can identify which of the residues are affected, but you can also find out what is the binding affinity, what is the stoichiometry of the binding, and what is the exact binding site on the protein. And this can then be used to model the structure of the protein-drug interaction.
Hello, my name is Michael Treyer and I'm working in the computational structural biology group here in Utrecht. So we got some 3D structure from the NMR experiments. What we are going to try to do is to visualize the structure and see if the structure is good and how we could maybe improve it. So we got this protein in green, and we got also the residues that are considered as active, as important for the interaction with the drug we studied. These residues are highlighted in orange and red. The orange one being the residues that are okay according to Earth, and the red one being the residues that might be sort of problematic for the 3D structure. And if we go a bit closer, we can see that this residue of the protein on the ligand, the drug here in blue, are clashing. They are too close from each other. And it's quite problematic because in real life, two molecules cannot touch each other when they interact. They always have some distances between each other. So what we are going to try to do here in the computational structural biology group is to refine the structure. We got some other structure, what we call the refined model, that seems to be much better. So here, no red residues anymore, so apparently no clashes. We can see that the distances we calculated are quite okay. So this structure seems quite okay. It is more stable than the previous one, so most likely to be the one that we find in a cell.
Hi, my name is Nathaniel Martin. I work in the Department of Pharmacy here at Utrecht University, and one of the aims of my research is the development of new antibiotics, specifically antibiotics that will work against drug-resistant bacteria. And some of the approaches we take are actually very much dependent on information that's been obtained using NMR to understand how antibiotic molecules can interact with bacteria and with molecules that bacteria rely on. And one of the most important molecules in this regard is the molecule you see here, the lipid 2 molecule. Lipid 2 is a molecule that bacteria use to make their cell walls, and importantly, it's a molecule that we as humans don't use. So if you can interfere with either the synthesis of lipid 2 or the way that it gets used by bacteria in making their cell walls, you can potentially have an antibiotic that selectively targets bacterial cells and doesn't touch human cells. And the starting point for the work that we're doing in my group centers around the molecule you see here. This is called niacin. Niacin is a naturally occurring antibiotic. It was actually discovered the same year as penicillin. And what was important for us was a report about 10 years ago now out of Utrecht, people working in the chemistry department and the NMR department, who found that the niacin molecule specifically binds to the lipid 2 molecule that bacteria rely on in the way indicated here. This part of the niacin molecule, this part highlighted in blue, specifically binds to this region of the lipid 2 molecule. And based on this information, my research group has worked on designing variants of the niacin molecule that are more drug-like. Here you see an example. And we start from the full-length molecule and we cleave off this bit, we keep this part, and we modify it to contain a small lipid. And these molecules are active as antibiotics. They kill many bacteria, including drug-resistant bacteria. And here you see also a nice bit of microscopy which shows if you have a drug-resistant cell, it grows normally, and when you apply our antibiotic, you can see the cells are dramatically destroyed. And again, the important starting point here was an NMR study revealing how the niacin molecule binds to the bacterial molecule lipid 2. So again, a very strong and important indication of just how key NMR studies can be in drug development.